Hi everyone. First of all, apologies for my voice. Today in class, I want you to cover work on an introduction to the normal distribution. And at the end of this session, I want you to work on exercise 16A from your textbook. First of all, what does the normal curve look like? The most common continuous probability distribution is the normal probability distribution. The normal probability distribution is one type of continuous distribution. It looks like this. No doubt you would have seen it before. And the key features are it's symmetrical, it's bell-shaped and in fact known as the bell curve. It's single-peaked or has one maximum value or one peak. The total area under the curve is equal to 1. And like a continuous probability distribution, the probability of x taking a value within a given interval corresponds to the area under the curve in that given interval. Okay, there are two important parameters concerned with the normal distribution. One is the mean and the other one is the standard deviation. And they are very important to the normal distribution. The mean is always denoted as mu, this symbol here. This is the Greek letter mu, and it looks like this. In probability, it's always used to stand for the mean. As you already know, the standard deviation is denoted as sigma. And in a question involving a normal probability distribution, the mean, or mu, and the standard deviation, or sigma, is always given to you. With the normal distribution, we always use the following syntax. It looks like this. It says x follows a normal distribution with a mean of mu and a variance of sigma squared. Remember, sigma squared is always the variance of the distribution. Now, with a normal distribution, the mean determines the centre or the peak of the distribution or the curve, and the standard deviation determines the width of the distribution or the curve. Let's have a look at the normal distribution. You can see the bell-shaped curve here, and the mean, or mu, is situated exactly in the middle of the curve, and it corresponds with the peak up here. The standard deviation also has a role in the curve. You can see here that the y-coordinate of the peak, the x-coordinate is mu, the y-coordinate is this value over here. It's 1 over sigma times the square root of 2 pi, where sigma is the standard deviation. Okay, how does the mean determine, or what effect does the mean have on the curve? Well, the mean determines the location of the general curve. We'll illustrate with this example here. Here we have two different distributions, distribution 1 in blue and distribution 2 in red. Over here is a key. You'll see that the key is telling us that the sigma of the first distribution, the blue distribution, is equal to sigma of the second distribution, or the red one. In other words, the two standard deviations are the same. You'll notice in looking at both of these curves that they are both the same width, because the standard deviation determines the width of the curve. However, the means are different. The mean of the first distribution, the blue distribution, is less than the mean of the second distribution, the red one. And you'll notice when you look at the curves, they're in different locations. The second distribution is to the right of the first distribution, and that is because the centre of the distribution, the mean, is greater in the second distribution than the centre or the mean in the first distribution. In summary, the mean determines the location of the general curve. Now, the standard deviation, on the other hand, determines the width of the general curve. Again, we'll demonstrate with this example. Again, we have two distributions here. The blue curve is distribution 1, the red curve is distribution 2. And over here in the key, we are told that the means for the two distributions are the same, but the standard deviation of the first distribution is less than the standard deviation of the second distribution. So when we look at the two curves, we can see that the peaks, or the centre of the distribution, are both located in the same place for the two curves. They're both here. However, the second distribution is much wider than the first distribution because its standard deviation is greater than the standard deviation of the first curve. The peaks of the two curves are higher. So the first distribution is higher than the second distribution. This is because the area under both curves is equal. The area under both curves is equal to 1. So if the area under both curves is the same, the fact that the red curve is wider means that the peak has to be lower than the peak for the first distribution, because the first distribution is a lot narrower than the second one. In summary, the standard deviation determines the width of the general curve, and the mean of the distribution determines the location of the general curve. Let's look at the equation of the general normal curve. It looks very complicated, but it's not really. Here is the equation here. Let's analyse it. 1 over the standard deviation times the square root of 2 pi times e to the power of -1/2 x minus the mean over the standard deviation, the whole thing squared. So in this equation, we have our two main parameters, sigma and mu. We have our random variable x, which is here, and we have the constant pi. In most cases, when you are given the mean and the standard deviation for a distribution, the standard deviation will be inserted here and the mean will be inserted here. Let's look at some examples to illustrate what I mean. Here are equations for 4 different normal distributions. In this example, the standard deviation here is 5. You can see it at this value here, and you can see it at this value here. And the mean is 8. You can see it located here. In this example, we have a mean of 2. However, there doesn't seem to be a standard deviation. Well, the fact that there's nothing here means that the standard deviation is equal to 1, and this implies that this whole expression here is over 1. So the standard deviation here is 1. If we look at this example here, we have a standard deviation of 4. It's located here and here. There doesn't seem to be a mean. This implies that x minus 0 is here, so the mean here is 0. In this one here, we have a standard deviation of 2, here and here. Now, my mean here is -3 because this implies that we have x minus -3 to give us x plus 3. So in general, the features of the general normal curve. It's symmetric around the line x is equal to the mean. The line y is equal to 0 is a horizontal asymptote. Almost all of the area under the PDF lies within 3 standard deviations of the mean. The total area under the curve is 1. The mean, median and mode of the distribution are the same. and the probability that x takes any value in a given interval will be found by finding the definite integral of the function between those two limits. All normal curves which contain a mean and standard deviation are different, but they can be reduced to the same normal curve. So when we reduce the general normal curve to a standard normal curve, the equation now looks like this one. Notice how we don't seem to have a standard deviation or a mean in here. It looks much simpler. This is because for the standard normal curve, the mean is 0 and the standard deviation is 1. The features of the standard normal curve are very similar to the general normal curve, but they revolve around a mean of 0 and a standard deviation of 1. So it's symmetric around the line x is equal to 0. The line y is equal to 0 is a horizontal asymptote. Almost all of the area under the PDF lies within 3 standard deviations of the mean. The mean, median and mode of the distribution are the same and are equal to 0. And all normal curves which contain a mean and a standard deviation are different, but they can all be reduced to this same normal standard curve. In summary, here we have the equation of the standard normal curve where the mean is equal to 0 and the standard deviation is 1. And here is the equation of the general normal curve where a mean is given as a certain value and the standard deviation is given as a certain value. Okay, transformations come into these curves as well. The standard normal density function is the basic function for the normal distribution. The general normal density function is a transformation of the standard normal density function using 2 dilations and a translation. First of all, we have a dilation of 1 on sigma from the x-axis. That's the vertical dilation. Then we have a dilation of sigma from the y-axis. This is a horizontal translation. Finally, we have a translation of mu in the positive x direction when the mean is greater than 0, or if the mean is negative or less than 0, there's a translation of mu in the negative direction. Sorry, up here I should have said that there was a horizontal dilation of sigma. Let's look at this example. We have this general normal density function given to us, and we want to first of all write down what is the mean and standard deviation of the general normal probability function, and what transformations have operated on the standard normal curve to produce this curve. Well, first of all, here we can see that the standard deviation is 3 from this value here and this value here, and the mean is 2. With regard to the transformations, we have a dilation of 1 on 3 from the x-axis, and we have a dilation of 3 from the y-axis. We also have a translation of positive 2 units in the x direction. If we're asked to sketch the curve of the function, it would look like this. Notice with the mean being 2, the centre of the distribution or the peak is located at 2. And because the standard deviation is 3, I have the curve spread over largely 3 standard deviations. So we go up 1 standard deviation to 5, 8 and 11, and down to -1, -4, -7. Finally, I want you to do exercise 16A.